All right, hello everyone. So this is the second part of that lecture number one, where we were reviewing some of the fundamental concepts. In the past lecture, part of the lecture, we reviewed resistor, Ohm's law, Kirchhoff's current and voltage laws, voltage current divider circuits, and the Norton Thevenin equivalent circuits briefly. In this part, we are gonna very quickly talk about inductor and a capacitor. And then we're gonna officially start our course starting next lecture. Okay, so again, a very quick brief overview of what an inductor and a capacitor is and what happens in terms of its VI, terminal characteristics. So here are some of the pictures or the examples of the inductors. At the heart of it, inductor is a coil of wire. And what happens is when you flow current, for example, once you're going to flow the current through that coil of wire, it is going to produce a magnetic field, which is essentially is Ampere's law. So if you're going to provide more current, more stronger magnetic field, and the energy stored representatively in the magnetic field, so higher energy stored, right? So you apply a current to the coil of wire, which behaves as an inductor. That current produces a magnetic field around the wires by Ampere's law. At the same time, another thing is happening, and that is electromagnetic induction or Faraday's law. So essentially the idea is that once you're going to apply this current is not going to reach its final value. Even if you have applied a DC current, it is going to take a little bit of time where it is still changing, right? Or increasing, for example. So as that current is changing, the magnetic field that was produced around the wire is also changing. And Faraday's law states that the changing magnetic field should induce a voltage. And that is the voltage or the terminal voltage across the inductors. So a changing current produces a changing magnetic field, produces a voltage. And according to Lenz's law, that voltage is the polarity of that voltage is kind of in terms of opposing that the original change in the magnetic field. This has a very important implication, and that is the voltage across the inductor appears only when there are changes in the current. If the changes in the current will stop producing the changes in the magnetic field, that would stop producing the voltage across the inductor. And practically speaking, once the changes in the current will become zero, the voltage across the inductor will become zero and will become a short circuit. We're going to talk about that in a second again. Okay, so again, this is an inductor. Here are some of the kind of key features of an inductor. Again, we talked about it's an energy storing element. It may or may not have a ferromagnetic course. In case of ferromagnetic course, the inductance value of that inductor essentially increases. The unit of the inductance is Henry, and they are usually rated for the maximum current it can allow passing through it. So let's talk a little bit more about the inductor. Here is the symbol of an inductor, you should know from the previous course, and here is kind of the terminal VI characteristics of the inductor, right? And you already know that this is the VI equation of an inductor. This voltage that appears across the terminals of an inductor is proportional to the time rate of change of current. And why? We just talked about this. We apply a current that produces a magnetic field around the coil, right, which is an inductor. And that, as long as the current is changing, the magnetic field is changing, which is producing the induced voltage V. So let's suppose that you have a DC current source to start with the inductor, right? And that DC source is going to provide current to an inductor in that transient period, sorry, which will produce the changes in the magnetic field, produces the changes in the current will produce the changes in the magnetic field, which is going to produce a voltage across the inductor, right? So what is going to happen once those transients will settle down, or once you're going to reach a steady state value? In a DC source, very quickly you are going to reach a steady state value, the final value, which will become constant. That constant means that the changes in the current will become zero. As soon as the changes in the current will become zero, your voltage, induced voltage across the inductor will become zero. If the voltage across the inductor will become zero, practically means that at a steady state, once transient settle and the final current value is reached, the inductor behaves as a short circuit. This is really the crux of what you need to remember going into the course, right? Starting with this equation and some of this thing. So we already know what is the voltage across the inductor. Let's find out the current across the inductor. So we are going to do kind of a very quick calculation. Then we're going to do kind of more complicated, similar differentiation integration calculations throughout, or at least for the next many weeks. So gets comfortable with that. So starting with this equation, V equals L di by dt. I'm going to take the differential on the other side. We get V times dt equals L times di. So essentially, let's do one more thing. Let's take integral on both sides, right? So interestingly, another thing that I'm going to do is I'm going to write this as L di by V times dt. Let's take an integral on both sides. So before I take an integral, I also need to put the limits of integration. And the point of putting the limits of integration on the left-hand side, we have a changes in the current, and on the y side, we have the changes in the time. So let's see, L, the changes in the current are happening from I t naught to I times t, whatever that final time is. Another thing that I'm going to do is, since I'm using the variable I over here, I am following the notation of a book so that once you're reading a book, you don't get confused. I am going to change this variable of integration from di to dx. It does not matter, it's just a variable of integration. The limits of integration matter once we are going to change it, right? So this should be equals to, again, our variable of integration was dt. So I am going to put the limits of integration from 0 to time t. And then I can change my variable of integration from dt to d tau. So once I get this thing, and I changes my limit of variables of integration to limits of integration and just swap and kind of comes up with any new variables to avoid the confusion. So once we do that, we can just solve this equation very quickly, right? So for example, you would get over here, I'm also going to take L on the other side. So you would get I of t minus I of t naught equals 1 over L, 0 to t, V of d tau. So your I of t becomes 1 over L, 0 to t, V d tau plus I t naught. So here is the equation of the current, the current that flows through the inductor. Another important point is in most of the applications, the T naught is the initial time, right? So when it's kind of our initial condition, we call this time T naught as initial condition. And in most of these cases, what we do is we consider this time T naught as 0 seconds or 0. So we can also kind of rewrite this entire equation as 1 over L, 0 to t, voltage, d tau plus I of 0. So here is the value of the current, and here is the voltage. Now I'm going to derive a couple of other parameters with respect to inductor. So for example, the thing that I'm interested in is the power and the energy. So based on the voltage and the current, we can easily derive the power and the energy, right? We already know that power equals V times I. I already know the equations of V from the last slide, L di by dt. And I also know the equation for the I, which was equals to, what was the previous line? 1 over L, okay. So 1 over L, T naught could be 0 to T, V times d tau plus I of 0, right? So this was equation. So we can put both of these equations over here. So first one is power equals VI. One of the representation is you can just take this equation and multiply this with a current. You get L times current di by dt. Another equation for the power is where you can use a current equation here, right? And you use the voltage value V and replace the current value here. 1 over L 0 to T V of d tau plus I of I naught, right? So here is the power equations for the inductor. Similarly, in terms of the energy that is stored in the inductor, for in order to find the energy stored in the inductor, again stored in the magnetic field, and how we apply current that produces a magnetic field, the changes in the current produces a change in the magnetic field that induces a voltage V, right? If there is no change in the current, no change in the magnetic field, no, and V becomes zero, right? And we can see it actually over here. If di by dt becomes zero, the V becomes zero. Okay, coming back to the energy. So we already know that the power is the time rate of change of energy, and W is over here energy stored, right? And power is also equals to over here. I'm going to use this equation, L I di by dt. If I'm going to use this, I can, of course, I can cancel dt from both sides. I can say dw equals Li di, right? And similarly, I can further here we have a variable of integration with the energy. Here we have a variable of integration with the current. So we can take integral on both sides. Over here, I can put limits of integration, since this was the energy. So from 0 energy to W energy, and I can replace the variable of integration to anything. Could be xy, for example, d of x equals L times, we have a current. The limits of integration on the current should be starting with current 0 to all the way to current I. And I'm going to replace that. You can keep this I, or you can replace again I with any other variable. Let's keep it. Or in the book, for example, they have replaced I with Y as well. So you could have easily done that. Again, once we're going to take integral on both sides, what we are going to get is essentially W minus W of 0. W of 0 is 0 equals L. Again, 0 to I is I square over 2 I di. If you are going to take an integral, and this is going to come out to be 0 to I. Okay, so this should be L, and then I square, you're going to replace it over here. I square divided by 2 equals W, so you get W half Li square. So here's the amount of the energy that is stored in an inductor. Okay, so this is how you can easily derive it. Important thing again, these integrals and differentiations are going to be very common in throughout the rest of the course. We're gonna do it very frequently, so please get comfortable with that. The only one small nuance, and I would be more than happy to individually talk to you if needed. Again, this is how the author in the book is changing or replacing these variables of integration. Okay, and we can talk more about it, but this is how you can very easily calculate the value of the energy, the power, the current, all from originally starting with the value of the voltage across the inductor. Okay, now let's do a quick recap of capacitor. So what is a capacitor? Here are some of the kind of common capacitor examples. So for example, I think this is 1000 microfarad. Right, this is 10 microfarad. Okay, so you can easily buy these capacitors, very easily, commonly available. You're going to use many of these capacitors in your lab work as well. Very quickly, let's talk about what a capacitor is. So here's an example of a parallel plate capacitor. Essentially what capacitor is, you have two conducting plates or parallel plates. You apply voltage to it, and these are separated by the distance d and separated by either a dielectric or the insulator in between those plates. So as soon as you're going to apply a voltage across the capacitor, the charges will be accumulated, right? Over here positive charge, over here negative charge. So you are going to get a positive charge, positively charged plate and a negatively charged plate. So once you're going to accumulation of these charges will happen on both plates, what is going to happen is you're going to have a electric field established in between the plates, right? And this is where the energy is stored, right? So you're going to have this energy stored in the electric field. So higher the voltage value, higher will be the energy stored in the capacitor, or the capacitor gets charged. Now, the important thing, once you are applying a voltage, the charges are being accumulated, the energy electric field is being established, energy is being stored, right? The current per se does not flow through the capacitor. However, a current is established which is called as a displacement current. And what exactly is that? Is that current, or what happens? Right? So as long as your battery or your voltage is changing, as long as you have a positive d over dt, you have a time rate of change of the voltage will produce a time rate of change of charges on the plates. As long as this is true, the displacement current according to Maxwell will remains true, right? Once you're, if you have a DC voltage source, and once that reaches a final value or the steady state, the changes in the dV by dt, or the changes in the voltage with respect to time, will stop, and this will stop changes dq over dt, or the time rate of change of on the plates of the capacitor that is shown over here. So once dV by dt becomes 0, or dq by dt becomes 0, the amount of the current, that is the displacement current that is flowing through the capacitor, will become 0 as well, right? So once the charging stops, the current stops. And this is a very interesting implication, right? So you connect a battery to an uncharged capacitor, the charges are being accumulated, there is a change in the voltages, changes in the charges, the current is established. As soon as the voltage reaches a peak value, the capacitor is fully charged, the current will stop, and the capacitor is going to behave as an open circuit. Important point, okay? So, interestingly, we already know that the amount of the charge accumulated equals to the capacitance value times the voltage, applied voltage. And you can, for example, differentiate it with respect to time. So dq over dt is c dv by dt. And we already know that this dq by dt is equals to current, right? So this is how we can find the equation of the current, right? So this is what I just did. The other point that I mentioned in the previous slide, that once your changes in the voltage with respect to time become 0, right, then your current will become 0 as well. And this happens at a steady state. Again, as soon as you apply a DC source for a brief time, there is a change in the voltages, right? Your voltage is trying to get to the final value, the steady state value. During that time, dV by dt, this thing, the time rate of change of the voltage is positive. So your current, there is a displacement current. This rate of change of voltage also produces a rate of change of charges accumulation on the capacitor, and that is why your current is positive. As soon as that will become dV by dt becomes 0, dq by dt becomes 0, and the current becomes 0. And practically your capacitor behaves like an open circuit. This is an important consideration, and we're going to talk about it a lot. So don't worry, this point will become more clear in the upcoming lectures. So key points are, again, capacitor is an energy storing element. It stores energy in the electric field. It has a memory. Again, what does that mean? This is going to become more clear in the next lecture. Let's say you charge a capacitor and you are going to remove that voltage source which originally charged the capacitor, right? The charge accumulated won't become 0 right away at that instant. what is going to happen is capacitors have memory, it stored the energy, so it is going to take time um, to discharge. Once the capacitor gets charged, for example, if there's a resistor or some sort of a load, then the capacitor is going to get discharged in a certain amount of time. And this is what we are going to learn in the next lectures as well. The capacitors are usually rated by the maximum voltage that can tolerate them. And again, we talked about this in a steady state. The capacitor becomes an open circuit because in a steady state, the voltage rate of change of voltage becomes zero. So our current becomes zero. So let's drive some very quick equations for the capacitor as well. Again, here the symbol of the capacitor, the positive terminal and the negative terminal. Here is the terminal voltage and the currents. Here is the equation that we saw in the previous slide. The amount of the current equals or depends on the time rate of change of voltage. So what I'm interested in is finding the value of the V. So in order to find the value of the V, essentially what I'm going to do is I'm going to take I times dt equals C times dV, and I'm going to move C over there as well. So dV equals 1 over C I times dt. Again, we are going to do something very similar where we are going to replace the variable of integration and move I and T as the limits of integration and replace them with some other variables, right? So again, for the voltage, in terms of limit of integration, voltage goes from 0 to some time t. dV equals 1 over C, and current goes from, and sorry, time goes from t naught to all the way to t, right? And this is I times d tau. And again, you can again replace this to x or some other variable, x. Okay, so this comes out to be V of t minus V of 0 equals 1 over C. T naught is initial time, which can potentially be 0 all the way to t, I times d tau. And I can further replace it with, take V of 0 on the other side, IC 0 to t. Again, this is t0, t naught, which is usually 0. So we can practically put 0 here. I times d tau plus V of 0. So here's a equation. This is how you can drive the voltage equation across the capacitor. Similarly, we can do the power, find the power across the capacitor as well. Exactly the same way that we did last time, right? So power equals V times I. So we already have, for example, this equation. And I can put the value of the V over here. So I can get CV dV by dt is one of the ways we can represent the power. Another ways is that we can represent the power where I can use this equation over here and use the current I times 1 over C t naught to t I of d tau plus V of 0. So here is another equation for the power. Similarly, you can find energy in the capacitor as well. If you remember, we talked about this. The power is a rate of change of energy. Energy is being represented by W over here. And I can use this equation over here, CV dV by dt. And again, dt's can be cancelled, so you are left with dW equals CV dV. I can put the limit of integrations here, 0 to W, and replace the variable of integration. And then we are left with C, 0 to V, and then we have dV here. So that is why your initial voltage is practically 0 all the way to V. And we can also replace this variable, V variable by Y, once we are taking integrals on both sides, right? So we got W minus 0 equals C y square over 2 times 0 to V, and you can replace V over here. So you get C V squared divided by 2. So W is half CV squared. So here's an equation for the energy that is stored in the capacitor. And finally, here is some important equations. I think you already remembered that, but just to give you kind of a summary on a single slide. We talked about resistor in series. When the resistors are connected in series, the total resistance is the summation of all of that. When the resistors are connected in parallel, the total resistance is the inverse of 1 over R1 plus 1 over R2 plus 1 over Rn. The same thing happens with the inductances. When the inductors are in series, the total inductance is the summation of all of them. And the total inductance is, when they're connected in parallel, is similar to the resistance, 1 over L1. Or you can also write it, right? L total is 1 over L1 plus 1 over L2 plus 1 over L3, right? However, capacitors, and in terms of if you want to remember or memorize this thing, capacitor behaves, the addition or the equivalent capacitances behaves kind of opposite to the inductors and the resistors, where if the capacitors are connected in series, the total capacitance is calculated in this way, and if they are connected in parallel, then the total capacitance is the sum of all the capacitances, right? So I hope that you will. So this thing should be remembered or memorized, or I don't think so that you need to memorize it. You should remember it by now by taking the previous PE1 course. So with that, we are going to finish this lecture. Some of the take-home messages of this lecture, right? Inductor inductor is just a coil. You apply current to it, which produces a magnetic field. The changes in the current produces changes in the magnetic field. By Ampere's law and by Faraday's law, there is an induced voltage, right? And so the voltage can only be induced once there are changes in the current, right? So if there are no changes in the current, once the current reaches a steady value, the voltage across the inductors becomes zero, and it becomes a short circuit. So that is why the inductor can be replaced by the short circuit in a steady state condition. Similarly, for the capacitor, the changes in the voltage produces the time rate of change of the voltage, or changes in the voltage produces the change in the charge accumulation, which produces the displacement current. So if the voltage has reached a steady state value to charge a capacitor, capacitor has been charged in the steady state value, then the rate of change of the voltage becomes zero, and the I becomes zero as well. So the current becomes zero through the capacitor as well. And the capacitor behaves as an open circuit. So this is very important. So I hope that this is one of the take-home messages, and how you kind of solve both of, for example, how do you solve these equations? We are going to do a lot of the derivations, right? So you should take it as an example. For example, in this inductor case, we started with this V L di by dt, and then we apply this integrals on each sides. So also remember some of these things, and we are going to take it from there. So with that, thank you so much. I will talk with you in the next lecture. That's pretty much it in terms of the kind of a recap of some of the main elements. We are going to delve more deeper into the actual course content starting next lecture. Thank you. Bye.